One special case for 2x2 two-way tables is to do a 2-prop z-test. It's a different calculator test on your calculator. So for example, let's imagine that we didn't look at 3 or more color dogs. We only tracked the 1 color dog and the 2 color dogs and cats here. So here, 1 color, 2 color, cats, dogs. In each direction, each categorical variable has exactly 2 options. So this grid is 2 by 2. When you do that, you are no longer forced to use the chi-squared test. You can actually use a 2 proportion test. And then in a second we'll look at using the 2-prop test just from like a paragraph description instead of from a table like this. If you were to use the chi-squared test, you would get a p-value of 0.023. Let's try using this with the 2 proportion test. Now there's a few different ways you can turn this into proportions. First, you have to define something to be success, and then you have to figure out what the 2 separate options are going to be. And I'll do it 2 totally separate ways just to show you both. Let's imagine that one of them focuses on 1 color and the other focuses on 2 colors individually here at a time. And let's define dogs as success and cats as fail. Now I'm only doing that because I'm a dog person. You could totally flip those and get the same answer. So success would be 35 out of 128. That would be your proportion right here, your first proportion. And over here, 2 colors, same thing, success out of the total. So 33 out of 78. So those are my 2 proportions. And the thing that I'm going to do with these values is put them into my 2-prop test. So I go to Stat, Tests, and the 6th one down here, 2-prop z-test is what I'm going to use. So my x1, the numerator, a number of successes, is 75 out of 128. My x2, number of successes in my second proportion, would be 33, and it would be out of 78. Now I'm going to choose to do a not equals test. There are other options, but for this one I want to do the not equals test, and I want to calculate my p-value. Now you're going to notice that there's p's all over this thing. We have p1 not equal to p2, then we have a p, we have a p hat 1, a p hat 2, a p hat, all kinds of stuff. The one that we care about is the one that has no special stuff on the p. It's just the regular p-value right here. And what you'll notice is it's exactly the same until you get up to the very upper decimals as the p-value we calculated with chi-squared. And that's pretty remarkable given that these are completely different tests done in completely different ways, totally different formulas that don't even resemble each other. So to get almost exactly the same value means that it's measuring really the same type of thing. So our 2-prop z-test, if we break it down this way, would get us these results. Let's break it down a totally different way for a second. Let's look at it, instead of dogs and cats being success versus fail, let's look at the 2 separate proportions as dogs is 1 proportion and cats is another. And let's arbitrarily say that 2 colors means that you're successful and 1 color would be failure. So 33 out of 108 would be considered success. So that means that of the dogs, 33 out of 108 were successful because they were 2 colors. And for the cats, 45 were successful because we arbitrarily said 2 colors is going to be successful. So 45 out of total number of cats, 98. These are completely different proportions, but yet if you take the time to put this into your chi-squared or your 2-prop test in your calculator and do a not equals test between the proportions, you'll find that you get the exact same p-value. So it doesn't matter which way you look at the table, you're going to get the same results. But it's not just a shortcut for chi-squared. The thing with chi-squared is you have to do the not equals test to be comparable to the chi-squared test. But when you have a two-prop test, you also have the option of doing greater than or less than. Also, when you do two proportions, you can find confidence intervals of the difference, and we'll do that later too. So the two-prop test gives you a lot more power with the situation you're working with than just a typical chi-squared. So let's look at this new case. Is free throw percentage affected by whether or not you wear socks when shooting your free throws? Let's imagine here we have some data. We have a player takes 100 shots with socks and makes 72. She also takes 100 shots without socks and makes 61. Is she better without socks? Well, clearly not. So I would say, maybe let's rephrase this, is she better with socks? Yeah, I would say it looks from here that she's better with socks, but we haven't statistically proven it. Is it beyond a statistically reasonable doubt? Let's figure it out. The first step is to set up our hypotheses and choose our alpha value. The next step is make sure that we have our minimum conditions met, and these are very similar to chi-squared minimum conditions. And the third thing is to actually run the test. So we have our data. In order to set up our null and alternative hypotheses, we need to have some symbols to represent everything. When you're doing a two-prop test, you have two proportions, each of them represented with p. And since your null hypothesis always has things equal to each other, the null is going to be that one of your p's is equal to the other one. They are equal. Now, when you have these and you have two proportions, it's hard to know which one corresponds to what. So I like to give them a little label, such as socks or no socks, so I can tell them apart. I might also like to throw a number in there, like 1 corresponds to socks, and 2 corresponds to no socks, or without socks. That way, I know which part to put these into in my calculator. So if that is 1, this one's 1, the one below is 2, then when I go to type these numbers in my calculator later, I'll be very organized and know what represents what. So it's all about staying organized at this stage in the game. Our alternative hypothesis is going to be exactly the same thing that we wrote for our null. So I'm literally just going to copy paste it right now. Except for our symbol between. We want to decide, is it greater than, is it less than, or is it not equal to the other proportion. Now, the question here, I'm going to change this question to, is she better with socks? So if we want to prove it that she is better with socks, or she makes more of them, then we would assume that making more, having a higher percentage, would be better. So we're going to assume that she is better with socks. And again, I changed this question because I intended it to be with. I just made a mistake there. So usually you wouldn't just go up and change the question. The other thing that we forgot to do a second ago was to choose our alpha level. I picked the standard of 0.05. Now let's check for our minimums and label our actual numbers. We said P sock, with the proportion representing the socks, was going to be P1, our first one that we put in our calculator. And the numbers there were 72 out of 100. So 72 out of 100. And by writing this all down, again, it's just going to keep us organized when we actually do our calculation. Probability, or the proportion representing your shooting when you don't wear socks, is going to be our P2, and that's 61 out of 100. 61 out of 100. Now the minimum situation in the two proportion tests is that you have to have at least 5 successes and at least 5 failures. Now 72 is definitely greater than 5, and the number of failures here would be about 28. So that's also plenty more than 5. So in this case, we have nothing to worry about. Over here, 61 out of 100. Again, plenty of successes, plenty of failures, nothing to worry about. If we had, let's say, 7 out of 10 instead, then we would only have 3 failures. That wouldn't be enough. We would not be able to do the test. If you're having a hard time trying to remember and keep straight all your different rules, remember in chi-squared, most of them, at least 80% of the cells, had to have 5 or more. Now when there's only successes total, there's only 4 options, 4 boxes. In this type of table, they would all have to be at least 5. So it's really no different than the rules for chi-squared. At least 5 successes and at least 5 failures in each proportion. Last step, once you have all this information written down, is to run your 2-prop z-test on your calculator. So let's go to Stat Test. The 6th one down is your 2-prop z-test. And let's type in these values. So our P1 is going to be 72 over 100. Our P2 is going to be 61 over 100. We said that our alternate hypothesis is going to be that 1 is greater than 2, since SOC is 1. 1 is greater than 2. And then calculate. And as you see here, just keeping sure that everything is very straight and orderly is going to make this calculation step a lot easier in the end. So we do our calculation, we get our p-value, and we find 0.04968, so forth, which technically is less than 0.05. Not by much, but we'll take it because, you know, we're statisticians and we love to find significance in our data. So we have a significant result. We do reject the null hypothesis, and we would say that, yes, the probability or the proportion of shots made shooting with socks is greater than the proportion shooting without socks.